Chapter 4 or Module 4, Gyroscopic Instruments. Now, we're talking here about the attitude indicator, okay? Concerning this part, the gyroscopic instruments, which is mainly the attitude indicator, we've already covered a little part of that in the intro and we've explained how it works. Okay, so there might be a repetition, but follow through. It would be beneficial to get it on a deeper level in case it didn't make much sense before. Hopefully it would be understandable, more understandable this time. Okay, now as we see to the right, you have the anatomy of the attitude indicator made of the gimbal here, okay, the raw gimbal which rotates based on the bank of the airplane. You have the gyro, which is the part that as it accelerates, okay, as it rotates, it will remain on the horizontal position, okay, parallel to the horizon. That would be the reference, okay, and it will keep with it the horizon reference arm, which would be the reference based on which you can observe by looking at the attitude indicator whether the airplane is going up or down or pitching up and down, or if it's rolling to the left, to the right, and at which angle. The angle of rotation is also called the bank index. Okay? Now, so again, as we mentioned, this part, the gyro, will keep rotating, maintaining this arm horizontally. Okay? And as the airplane moves up or down, so if it moves up, okay, this part here, okay, this, or rather, let me say this, yeah, this part would be going down because this will be maintained upward, this part, okay? This axis, which is the horizon reference arm, would remain fixed, and the disc here would go downward if the nose of the airplane is pitching up, meaning it will place this orange line on the blue disc, on the blue part of the disc, indicating a nose up. Meanwhile, during a dive, it would go upward, which means that the orange line, it would be placed on the brown area, indicating that the nose is pointed to the ground. It's pitching down. Also, during roll, the horizontal arm would remain fixated by the gyro because it's rotating at high speed. So this arm would remain fixed. However, the entire instrument, like the raw gimbal, yeah, the gimbal would rotate, okay, indicating a bank between the attitude indicator or the airplane and the horizontal line, horizontal reference line. So, gyroscopic instruments operate based on the physical behavior of a rapidly spinning mass, which is the gyro over here. A gyroscope consists of a rotor mounted in gimbals. These are the gimbals here, the pitch gimbal and the roll gimbal. Okay, so the aircraft would be rolling in reference to the gyro to the right and to the left. That would be the roll gimbal rotating right-sided or to the right side or to the left side to indicate the bank angle of the aircraft in respect of the horizon, and the pitch gimbal, which is to indicate the up down pitch, okay, or the nose up nose down movement. So when spinning at high speed, the rotor exhibits unique properties that are exploited in aircraft instruments. Okay, so the rotor, the gyro mainly, would be guarding its horizontal reference, okay, its horizontal position, and the gimbals would be for the raw gimbal rotating right side, okay, to the right side or to the left side, and the pitch gimbal would be rotating up and down in reference to this gyro. And this is how you get the indications of pitch up or nose up, nose down, and the rolling or banking angles. Now, The fundamental quantity governing gyroscopic behavior is angular momentum or angular speed, defined as L is equal to I, which is the moment of inertia, multiplied by the angular velocity. In other words, how many radians per second. Okay, how many radians per second this is rotating. The gyro is rotating. These are the quantities to be accounted for. So I multiplied by W would give us the angular momentum. A spinning rotor resists changes to the direction of its angular momentum vector. All right. So the spinning rotor, which is the gyro, it would resist the changes of bank, the changes of pitch. So the bank would be the right and left rotation of the rotating gimbals. As for the pitch gimbal, okay, it would be rotating downward and upward, not right side and left side. So this would be in reference to the rotor, giving us the measurements for the rotation gimbal. It would give us the bank, again, the angle at which the airplane is rolling to the left or to the right. And for the pitch gimbal, it would give you the degrees of nose up and nose down. So how many degrees is the airplane forming with the horizon when it's nosed up or when it's nosed down. Okay? Now, the thing is, which is the advantage and the necessity of the rotor, is that due to its rotation or rotating movement, it will keep steadily, okay, a rotation in reference to the horizon, because it has been rotating in that direction, so it will remain steady and parallel to the horizon plane, to the horizontal plane, which is the ground plane, okay? It would remain parallel to the ground, and that would be the reference in respect of the bank angle and in respect of the pitch up, pitch down motions. So that would remain as our reliable reference plane against which we measure these other parameters, again, such as the roll and the pitch. Okay, so it remains stable. It forms the basis for stable reference instrument used in aircraft attitude and direction sensing. So again, you have here the spin axis, the rotor on the inside, and two gimbals, okay? That would be, again, the pitch up and down gimbal, I believe. I'm sorry, that would be the roll gimbal, okay? And that would be the pitch up and down gimbal. All right. 4.2, rigidity in space and precession. Let's start with rigidity in space. So what are we exactly talking about? Rigidity in space is the tendency of a gyroscope, or the gyro, the rotating gyro, to maintain the orientation of its spin axis, the axis around which the rotor is moving, it's turning, relative to inertial space, regardless of the aircraft motion. So in other words, whether the aircraft is rolling, it's banking, is pitching up or down, the gyro will maintain the same heading, the same plane, okay? So the axis, in other words, the axis would remain fixated on the same orientation. It won't roll, it won't bank, okay? It will remain fixed thanks to a rotating gyro around it. So it will stay rigid in space. It doesn't matter what the aircraft is moving, where its attitude is going, okay? So whether the aircraft is banking or rolling or pitching up or down, the horizontal gyro, the gyro rotating horizontally, would remain steady and maintain the same axis of rotation. Okay, so it will stay in the same position. This is what rigidity is referring to. So in other words, this property allows gyroscopic instruments to provide stable references for pitch up and down, for roll and heading as well, because this same gyro is used within the directional indicator, like the compass, so to speak, okay? Directional gyro, in other words. Now, the effectiveness of rigidity in space increases with a greater angular momentum. So it will remain more solidly fixated in the same direction, or in other words, the axis of rotation, it would be more rigid, more stable. So in effect, it will provide more accurate measurements when you have a higher angular momentum, when it's rotating at higher speeds, which is achieved by increasing rotor mass or rotational speed, okay? Because the rotation has to do with the mass, okay? With the, the potential force. When you have a heavier rotor, it would stay more stable, more rigid in space as it rotates, okay? Because, by the way, the inertia, which is the I, okay, rotation moment, the I is equal to mr squared, okay? So when you have a thicker mass, it would rotate with a good inertial force, okay? The moment, that's the rotation moment. And when you have a longer radius, which effectively, okay, it will affect the mass as well, or when you have a higher rotational speed. So any external force attempting to tilt the gyroscope must overcome its stored angular momentum to affect the reading of the indicator on the inside, which is the purpose of having higher angular momentum, so as to guarantee a stabilized reference plane within the gyro, okay, in order to provide accurate measurements when it comes to different parameters that we've tackled before, that we've referenced before. Gyroscopic precession. So what is this phenomena about? When an external torque is applied to a spinning gyroscope, here it is represented as a wheel, and this is the external torque that is causing the rotation of the gyro. All right? The pull, and this is a weird phenomena, because the direction of the applied force, that you would suppose it would be the same direction of the torque itself, but instead the direction of the applied force would be 90 degrees in retard to the torque vector, okay? It would be at the right angle with the torque force. Instead, that would be the L vector that is illustrated in this picture. So this phenomena is called or known as the gyroscopic precession, in which the wheel, when it's rotating, okay, it would start to be pushed sideways instead of being pushed in the same direction of the rotation, or within the same plane of the rotating disc, which is very interesting. So, given an example, you have the rotating wheel here, which is spinning counterclockwise, meaning in the opposite direction of the clock needles. So, how to determine the direction and orientation of the force vector, of the precession force vector, which is also another name for the angular momentum directional. You would have, this is how you get it. So let's say it's rotating counterclockwise. We apply what is called the screwdriver method. In case, imagine that you are removing a screw from the wall, okay? The screwdriver would be rotating counterclockwise. However, the movement, the forward backward motion, would be going back, okay? The motion of the screwdriver itself, other than rotating, it would be moving backwards along with the screw as you remove it from the wall. Meanwhile, the opposite, okay, the contrary of that would be the opposite direction. So in case the wheel is rotating clockwise in the same direction of the clock needles, so if you imagine the screwdriver and the screw, they would be rotating clockwise and it would be pushing the nail or the screw forward within the wall along with the screwdriver itself. They would be both going inwardly toward or in the same direction of the wall. So it would be an inward force. So you notice that you would have an applied force instead of being intuitively in the same direction and plane of the rotating wheel or gyro in our case. Instead, which is counterintuitive, it would be applied sideways, 90 degrees to the torque itself. Only what is parallel to the torque force is the delta L, which is the change of the angular momentum. So the quantity by which we measure that gyroscopic precession is omega p, which is the precession angular velocity, is given by the torque, the applied torque that is causing the rotation of the gyro to begin with, divided by L, which is the angular momentum. Now, in aircraft instruments, controlled precession is intentionally used to align or indicate motion. Okay, so when you have a controlled precession, it would show us like, I think, yeah, it can be used within the turn indicator. It's used in the turn indicator to indicate that the aircraft is turning. Okay, now, by the way, there's a slight difference. We don't want to mix the keywords. There's a difference between banking and turning. Okay, because the aircraft might be banking, so it might be rolling at a certain angle, 10, 20, 30 degrees, but not necessarily turning. It would be going like this. Of course, now, since the weight itself become divided into two components, vertical and horizontal, it would start turning the airplane. But initially, it is banking, not turning. In order to make the turn more effective, you need then to apply the rudder, and this is when the plane would actually be going to the right or to the left, along with the banking motion. Actually, during the landing, in order to correct the heading of the airplane, the pilot usually only applies the rudder when you have a crosswind in order to stabilize or like to make sure that the nose is centered to the middle of the runway. He won't apply any aileron controls. The rudder would be the only thing that would be manipulated in such case. So, in the turn coordinator, and when indicating if the aircraft is going to the right and to the left by manipulating the rudder, like the measurement of this turn would be received or would be measured based on the gyroscopic precession being applied to the fan, especially when you have the small airplanes such as the Cessna, okay? Because when it turns, you would have the force being applied to the rotor. This is how you get values in the turn coordinator, in the turn measurements, okay, by measuring the force being applied to that rotor. Now, another thing, you have precession that would occur in instruments, but it's not favorable. Why? Because it would cause reading errors within the instruments and drift. For example, when you have the gyroscope, okay, due to the turning of the gyro, you would have a precession that will move the gyro along with horizontal arm, upward and downward. Okay, it has the tendency to do that. Meanwhile, it is not favorable. Why? Because I would need to have the gyro rigid and solid as possible. Why? Because this is the reference point for the roll and pitch. So I would want anything to move except that specific part. Now this is another illustration for the gyroscopic precession. Okay, if we see here, let's say you have a motion of a wheel rotating about an axis. Okay, now why do we have this axis seeming to be stranded or stretched in one way or another? This is a representation of the effect of the force that's pulling this axis in a specific direction. And this usually happens like this distortion, okay? Or not distortion, like, distortion of this axis is due to the fact that when this rotating wheel, for example, that's being held by this girl, if the girl would try to move it right-sided to the right side, the right side direction or to the left side direction. So if this girl would try to rotate the wheel, and I'm not talking about the original rotation motion that's already going. I'm talking about this girl moving her right hand backwards and her left hand pushing it forward, rotating the wheel like this, okay? In the in the horizontal direction. It's rotating in the vertical direction, correct? If she wanted to rotate it, to move it like this, it would resist this movement. Why is that? And we've already discussed and talked about this resistance of a gyro to be bent in one direction or another. Okay? Why is that? Because it's already rotating, so you have a force, which is the gyroscopic precession, pulling it in a specific direction. If you try to change, like if you try to move it, to rotate it horizontally, like to change its heading, the heading of the plane in which the wheel is turning, it would resist you. Why? Because you already have a precession force pushing it, in a specific direction. So you are going against that force, it would resist you. Okay? Why? Because it's still pulling in one direction and you're trying to counter it by making it pull in another direction. So when the wheel is turning at much higher speeds, this vector would be much stronger. It would even resist you more from and prevent you from turning the wheel, okay, from changing the direction of the wheel. This is basically the gyroscopic precession. I hope it became clear in this slide. Now let's go back to the attitude indicator. So the attitude indicator, AI or ADI, attitude directional indicator, also known as the artificial horizon. That's another keyword, by the way, which is important. It provides the pilot with a visual representation of the aircraft's orientation, okay, relative to the horizon. And the horizon would be guaranteed as a reference by the gyroscope, the rotating gyroscope, as we mentioned before. It displays pitch. Pitch is nose up and nose down, and roll information, and is one of the most critical flight instruments. Now, as a reminder, the pitch is, for example, here you have a leveled flight where this orange line is at the center of the disk, okay? It's neither in the blue zone nor in the brown zone, which means that the aircraft is flying level. It's neither pitching up nor down. It's horizontal to the ground. Now, when it goes upwards, and here you see these sticks, these dashes, you can actually get, by reading these dashes, the angle, the current angle of pitch, whether it's positive, if it's climbing, if it's nose up. So that line with this orange dot would be in the blue part of the disk. If it's nose down, which is pitching down, it would be in the brown area. That is, the measurement or indication of the pitch. As for the roll, this is the roll. So if you have a roll to the left, let's say, by 15 degrees, I think this would be 15 degrees, okay? So the orange line would be like this. That would be roll to the left of 15 degrees. All right? Now, you can have both a roll and the pitch at the same time, by the way. So the ADI typically uses a gyroscope with 2 degrees of freedom, meaning that it can go up and down to indicate, not the gyroscope is what goes up and down, but the area, the gimbal, the pitch gimbal that goes up and down, because the gyroscope disc would be rigid. This is the stable and fixed part of the entire instrument. And the other degree of freedom is the rolling. Okay, so the rotating gimbal would rotate around the gyro to indicate the roll angle or the bank angle, whether it is, yeah, you have the bank angle and the pitch up and down. Okay, these are the 2 degrees of freedom, allowing the rotor to remain fixed in space while the aircraft moves around it. Okay, this is the necessity and importance of the gyro. The instrument case, the casing of the instrument, is connected to the aircraft, correct? Causing the horizon bar to appear to move relative to the aircraft symbol. Now, what's happening is this is what is moving around, okay? Not because it seems to us that the aircraft symbol, which is the original line, the orange line, it appears to us that this is the part that is moving, but the reality is this is the stable or fixed part and everything is moving about it. Okay, so the external or like the surrounding blue brown disk is the part that is moving around this reference line. So the instrument case is connected to the aircraft, causing the horizon bar to appear to move relative to the aircraft symbol. Now, due to gyroscopic imperfections, the attitude indicator is subject to drift, okay, and must be periodically realigned. Okay, it would drift from its original position. Most instruments include erection mechanisms that apply small corrective torques to maintain the vertical alignment. Okay, so that it would remain aligned correctly. Why? Because as it drifts, and why does it drift? Due to gyroscopic precession, the actual gyro would start drifting from its position due to these forces pulling it upward or downward. Okay, so in order to maintain correct measurements, we need to readjust it from from time to time, every now and then. Heading indicator or directional gyro, which is DG for as a short notation. It provides directional information based on gyroscopic stability rather than the magnetic north of a compass, okay, or magnetic sensing, in other words. That's why it is less prone to errors. It is less susceptible to acceleration and turning errors, which can erratically displace the needle pointing to the north. Okay, so it's more stable, more reliable, more accurate. Okay, why? Because it is based or it relies on the directional or the rotating motion of a gyro, directional gyro in the vertical plane, which becomes the reference point of all headings within this directional gyro instrument. Okay, so this is how it basically works. The directional gyro operates with a gyroscope, again, constrained to rotate about not a vertical axis itself, like the gyro itself is rotating in the vertical plane about an horizontal axis. This is the error here. Okay, so the axis itself is horizontal, but the rotation plane, the direction in which this gyro is rotating, is vertical, which is opposite to the horizontal gyro within the attitude indicator, where it rotates in the horizontal plane, but the axis itself is vertical. So again, the directional gyro has like a rotation in the vertical plane, but its own axis is horizontal. And through its rigidity, okay, in space, it provides a stable heading reference, and compared or against this reference, all headings or all turns of the airplane would be measured to like assess the current heading. Okay, all would be referenced to that stable, rigid, vertically rotating gyro. Now, however, Remember that this reference cannot be solid 100% due to Earth rotation and other mechanical imperfections, like, for example, the gyroscopic precession factor. It would start drifting away from the magnetic north. Okay, so once you stabilize it in the beginning to the magnetic north, okay, it's reliable, but after a certain amount of time, it would start incurring errors. So it needs to be resynchronized to the magnetic compass. That's the only problem with the directional gyro. However, every now and then, when it's synchronized with the magnetic sensing compass, it will produce great results. Now, the apparent drift due to Earth's rotation is approximately omega E is equal to 15 degrees multiplied by cosine phi per hour. That would be the drift. And phi is the latitude. Okay? Phi would be the latitude, or like the position on the Earth, okay, horizontally. That would be, again, yeah, like it's a reference angle, okay, on positionally on the face of the Earth, okay, in respect of an original reference position, which I think, yeah, in the middle somewhere of the globe, okay. That would be the latitude. Actually, the latitude is measured in reference of a middle point. I'm not sure if it's Greenwich or something, okay, but you get what is being inferred here, what's being referred to. Turn and slip indicator and turn coordinator. Okay, so this device, turn and slip indicator, uses a rate gyroscope that responds to yaw rate. Yaw being when the aircraft's rudder is turning to the right or to the left, pushing it sideways. Okay, so it's not the rolling itself. It is neither the banking. The banking and rolling are the same thing. It is pushing the aircraft sideways like the rudder of a ship. Okay, the rudder of the ship doesn't rotate the ship. Remember, it moves it sideways, either to the right if the rudder is going like this. It moves it to the right. Why? Because the water would be pushing the tail to the left. Or the exact opposite, if the rudder is going to the left, the air would push it to the right, would push the rear end or the tail of the ship, so to speak, to the right, which is called the stern, by the way. So the heading of the ship would be going to the left. It would be turning or leaning to the left. All right, this is how it works. So this is the yaw. Now, the gyroscope is mounted so that the precession occurs. Remember, we've spoken about the precession being the measurement tool, okay, like the measurement parameter rather, by which we can assess or like collect the data on the rudder movement and whether, like how much, not the rudder movement, but the movement of the yawing of the airplane. Yaw means the left or right movement, like the side right movement or left movement, again, just like the rudder of a ship. So the gyroscope is mounted so that the precession occurs in response to aircraft rotation about the vertical axis. The rate turned is proportional to angular velocity. Okay, that would be the rate turn. So angular velocity, the turn rate, I'm sorry, omega is equal to the true airspeed divided by the turn radius. That would be the turn rate, okay, or angular momentum. So omega equal V, which is the true airspeed divided by the radius of the turn, V over R. A bow in tube inclinometer indicates slip or skid by showing lateral acceleration. So you would have here a bow, okay, within a tube, inside a tube, inclinometer, okay, which is inclined. That would indicate if the aircraft is slipping or skidding. So if it's not turning properly, it would be slipping sideways. Meanwhile, okay, like, because why? Because if it's rolling but at the same time yawing, that would be on the center line. Why? Because it would be kept centered by the gravity. Meanwhile, if the aircraft is slipping sideways without rolling, so if it's not turning correctly, if it's only yawing, this would be indicated by the movement, the side movement of this ball within the tube to the left or to the right. Okay? The turn coordinator improves upon the turn and slip indicator by sensing both roll and yaw rates. Okay, its gyro is tilted relative to the longitudinal axis, allowing earlier indication of turn entry and exit. The turn coordinators provide better situational awareness during instrument flight and are particularly useful during standard rate turns. So if we go back to the image here, this is the turn coordinator. You would have a banking here during a roll, okay? So it would indicate how much it is turning, how much it is banking to one side or the other, all right? So it provides better situational awareness during instrument flight so that the pilot can be well aware on the angle or how much is the angle of the turn, if it's acceptable or if he's going above what is an acceptable limit for the bank angle, okay? If he's going like above the acceptable thresholds during a turn, whether to the right or to the left. Now let's dive deeper into how the turn and slip coordinator works. So at first, the turn and slip coordinator is not meant to measure the banking angle of an aircraft. It actually is used to measure three parameters, which are the direction of the turn, okay, the amount of the turn or the rate of the turn, that's second, so the direction, left or right, then you have the rate of the turn, how much it is turning, okay, how much is it banking, not the degree necessarily, but how much is it banking, that's second, and third, the quality of the turn. So if it has a slip on the inside of it, okay, if it's slipping or if it's turning correctly. If the aircraft is turning properly, so to speak, following a specific direction or changing heading to another heading, let's say from 30 degrees to 40 or 90 degrees azimuth. The azimuth is the horizontal angle, by the way. If it's turning properly, then it would be indicated within the inclinometer by this black ball that is within this tube. This ball would remain on the center position, okay? But if it's skidding, if it's slipping, it would be going leftwise, okay, or rightwise. That ball at the center. Now, going back to the anatomy of how it works, we need to dissect like the inner parts of the turn and slip coordinator. If you look at this picture to the left, okay, that would be the turn coordinator. So you have the gyro rotation, which is, by the way, inclined 30 degrees. If it's not like perfectly vertical, it's inclined at 30 degrees so as to detect two parameters, two changes, both the turn and the yaw. Yaw meaning if the aircraft is like heading rightwards or leftwards, like the rudder of the ship, okay? What the rudder of the ship does, this is the yaw. It yaws the ship, it doesn't roll it. It yaws it to the right or the left. Now, Again, this gyro is tilted 30 degrees, so it would be sensitive to both the yaw and the roll of the aircraft, and this is detected through gyroscopic precession. Again, you remember we referred to gyroscopic precession, where a rotating disk, due to its rotation, it would incur a force that it would be counterintuitive. You would think that the force would be going in the same vertical plane of the disk, but instead it would be pulling it sideways, 90 degrees from the direction of the rotation. Okay, so that would move the needle, which will be how the detection of the roll and yaw would occur. Okay, the precession itself would move the needle so as to indicate the roll and the yaw. This is basically how it works. This is when, if you remember, we refer to the gyroscopic precession as an important factor that would affect the roll and the banking, okay, within the instrument. You have here the turn and slip indicator, also another like the same thing, okay, a different flavor. You have the gyro tilted, like you would have the gyro rotation. It's tilted 30 degrees to detect both yaw and rotation or rolling. Vacuum driven versus electrically driven gyros. Here we're talking about different types of gyros. Let's start with the vacuum driven gyro. The vacuum driven type uses air suction in order to spin the rotor, typically powered by an engine driven vacuum pump. Okay? These systems are simple and lightweight, but vulnerable to pump failure. If the pump fails, then the entire system or instrument would fail. That is depending on the gyro or the rotation of the gyro, the gyroscopic motion. Okay, so in case of pump failure or contamination, the system would fail. Loss of vacuum pressure results in the gradual degradation of the gyroscopic indications, often without immediate warning. So it would gradually fall, okay? It would gradually start veering off course until it, the indication becomes completely erratic, but it would be a little bit late before you realize that the actual instrument had failed, because it is gradual and without any prior warning system. Electrically driven gyros. Now, electrically driven type uses electrical motors that would be powered by a current in order to spin the rotor. They offer more consistent performance, more reliable, faster startup times, so it would prime much rapidly than the vacuum driven ones that heavily depend on the air suction by a vacuum pump. This is how they work, okay? And they have an improved reliability, especially in multi-engine and modern aircraft. So electrical gyros are better suited for integration into electronic flight display. Why? Because you can actually detect a malfunction in this type, because it's driven by power, by electricity, and can be powered by redundant electrical sources. That's the beauty and the advantage of it. Meanwhile, compared to the vacuum type, the vacuum driven gyro, first of all, you don't have a warning system that can detect that the instrument had actually failed due to loss of the vacuum pump pressure. Okay. Second of all, it's not completely reliable due to contamination, and it doesn't have an enough past prime time. Meanwhile, for the electrically driven gyros, when you have a fault, it can be detected immediately on your instruments, on the display. Now, the operational comparison. Understanding the differences between vacuum and electrically driven gyros allows pilots and maintenance personnel to anticipate failure modes, to anticipate the failures before they take place and understand how these two different types can fail and apply appropriate emergency procedures to troubleshoot the problem or to execute a swift landing, an emergency landing. Modern aircraft increasingly rely on electrically driven and solid state gyroscopic systems to enhance reliability. Okay, so you can count on it. It remains consistent and stable throughout the flight, and safety, because you have early warning systems when you have an abnormal functioning or a detection of a fault.